Okay, this is the third video where we're going to work related rates example problems. And I want to note something about the previous video, which was part 2 of these example problems. So, for example, whenever we found the rate of change of the height of the pool, that was a challenging problem, one of the more challenging related rates problems. But what made it challenging had nothing to do with the calculus involved in the problem. What was challenging was coming up with a formula for the volume as a function of the water depth, the water height. If you weren't familiar with similar triangles, it would probably be hard to have figured that problem out on your own. But once we got the formula for the volume as a function of the height, then it was back to calculus. It's the same process as we did for every other problem. The volume function was a little more complex than like the Pythagorean theorem equations that we had come up with in other problems, but you just differentiate it and solve for the unknown rate you're looking for. And so, I mean, when it comes to like geometry, you have the Pythagorean theorem, but there's also like the law of sines, the law of cosines, that relates side lengths and angles of any kind of triangle, not just a right triangle. So if you had a problem, a homework problem, a test problem, well, this probably wouldn't be on a test. This would be too complicated for a calculus test, but a problem in real life, and to relate the two variables that you're trying to relate, you can't form a right triangle, but you can form another kind of triangle. Well, use the law of sines, use the law of cosines. It's going to be a little more complicated than like a right triangle. Like the formula, the law of sines and the law of cosines is a little more complicated than the Pythagorean theorem, or just like sine of theta is equal to opposite over hypotenuse. But so what if it's more complicated? It's the same. You know how to differentiate anything, pretty much anything. Like the law of sines is, you can differentiate the law of sines using the chain rule, no problem, and solve for the rate of change you're looking for. The resulting equation will be a little more complicated, but you get the equation for the variable you're looking for, the rate of change of the variable you're looking for, and then you just need to know how to plug in the known values appropriately. Do you make it negative or positive? Use the principles we talk about in all of these example problems to decide whether or not to put something as a negative or a positive value, and you got it. Okay, but anyway, let's get started. Gravel is being dumped from a conveyor belt at a rate of 30 cubic feet per minute, and its coarseness is such that it forms a pile in the shape of a cone whose base diameter and height are always equal. How fast is the height of the pile increasing when the pile is 10 feet high? So what rate do we know here? We have a rate that we know. We know that we're dumping 30 cubic feet per minute of gravel. So we know that the volume of this cone is increasing at a rate of 30 cubic feet per minute. Now, I don't know how realistic of a problem this is, like if you could do this in real life, but I guess if you wanted a rough estimate and you could see it definitely does form a cone, I don't know. So the volume of this cone is increasing at a rate of 30 cubic feet per minute. We know that, and we want to use that information to find how fast is the height of the pile increasing. So this is the height. Okay, so what is the formula for the volume of a cone? The volume of a cone is 1/3 pi r squared h. Okay, and you can see it gives us these two congruent lines here. And what this is saying is, it's kind of confusing, but the diameter here of the base is equal to the height. So 2r is equal to h. So we'll put this in terms of h, because that's the rate we're looking for. Wait. No. R is equal to h divided by 2. So there we go. Okay. So there's the formula that relates volume to height. And we're trying to find the rate of change of the height, but we have the rate of change of the volume. So there we go. So let's differentiate this with respect to time. So we get v dot is equal to, so bring down the 3 here. That's 1/4 pi h squared h dot. Now if we solve for h dot, we get 4 v dot over pi h squared. Okay. So h is going to be what? We're solving for when h is 10. And, you know, based on this formula here, it's just like another geometry formula. H couldn't be negative. There would be no circumstance where h would be negative. Volume could be negative or positive. Well, I mean, in this situation, it can. I mean, you can't unless they're pulling gravel out. But the volume is positive here, though. The volume flow rate, the v dot is positive here, right? That's what the problem tells us. So positive 30. Okay, so h dot then is 4 times 30 over pi 10 squared. So .382, and the units are going to be in feet per minute. So that's the answer. But if I was presenting this to somebody, I think it would be better to tell them that if we take 0.382 times there's 60 minutes in an hour, we'd say 23 feet per hour. That's more, to me, that's more intuitive. It's hard to conceptualize 0.382 feet per minute in your brain, or like visualize that, right? But 23 feet per hour, you might want to present it that way. That's equivalent to 0.382 feet per minute. 2 carts, A and B, are connected by a rope 39 feet long that passes over a pulley P. The point Q is on the floor 12 feet directly beneath P and between the carts. Cart A is being pulled away from Q at a speed of 2 feet per second. How fast is cart B moving towards Q at the instant when cart A is 5 feet from Q? Okay, related rates. There's a rate that we know, and then there's a rate that we want to know, and we can connect those two, not the rates directly, but we can connect those two variables with an equation. Yes, we connect the rates with an equation, but you're starting with the general variables. The algebra, you connect them kind of just purely algebraically, and then you use calculus and you differentiate to find the rates of change. So cart A is being pulled away from Q at a speed of 2 feet per second. So it's being pulled by something, like someone or something is pulling it. How fast is cart B moving towards Q at the instant when cart A is 5 feet from Q? And then the rope is 39 feet long. Okay, so what we know is, okay, so we want to have the dimension of A from Q and the dimension of B from Q. So we'll say this is A and this is B. We know the rate of change of A, that's 2 feet per second. How can we use that to solve for the rate of change of B? Well, we need to use some sort of equation to connect that connects these two variables. Well, it'll be some sort of geometry equation. We know that this is a right triangle, both of these. This is 12. We've got we have theta and alpha. Those are definitely two different angles, because you can see it's not symmetric. Let's see if we can we know the total length of this rope, so that's going to obviously be something that's going to help us here. So, and then the 12 is the same. So let's do this. Let's say that sine of theta is equal to what? Opposite over hypotenuse. That's, well, no, we'll say LAP, right? AP. Okay. Now, sine of alpha is equal to 12 over LBP. Now, you can see that LAP sine of theta and LBP sine of alpha, those are equal. Those are both equal to 12. So we can say that LAP sine of theta is equal to LBP sine of alpha. Okay, now we know that LAP plus LBP is equal to 39, right? The total length of the ropes, or the total length of the rope. Okay, I'm not sure how much this is going to help, so let's try something else. Let's see what the Pythagorean theorem does. Okay, we've got, so 12 squared plus a squared, the square root of that. Okay, so the square root of 12 squared plus a squared is this. Now, what is this equal to in relation to this? That would be 39 minus, and then the square root of 12 squared plus b squared. Yeah, there we go. Okay. Okay. 144 plus a squared is equal to 39 . So there's a formula that relates a and b. Now we can just take this derivative with respect to time, so we can find, and we know the rate of change of a, and we can solve for the rate of change of b. So how do we differentiate this with respect to time? Well, chain rule. What is the derivative of the square root of something? It's 1 over 2 times the square root of that something. But then times the derivative of that something. So I'm going to put, well, like, what's the derivative of 144 plus a squared? That's 2a. So this would be 1 times 2a. So let's just put the 2a up here. Okay. Then we have 0. Derivative with respect to time of 39 is 0. Same thing here. The derivative with respect to time of the square root of something is 1 over 2 times the square root of that something, and then times the derivative of that something. So then times the derivative of that something, 144 plus 2b is, that's 2b, and then times the derivative of that something, b dot. This is a dot, so I messed that up, right? So I said times the derivative of that something, so the derivative of 144 plus something squared. What is the derivative of 144 plus something squared? It's 2 times that something. Boom. Times the derivative of that something. dA dt is a dot, dA dt. And the same exact idea here. Okay, now we just need to solve for b dot. So, well, we can cancel this. B dot B and then So B dot is equal to B and actually I forgot there's going to be a negative here, right? There would be a negative because you add this to both sides, but to get these on opposite sides, there's going to be a negative. And okay, and then we have A dot. So there's an A dot. Let's just put it here. Okay, there we go. So now we just need to plug in A, B, and A dot and get the signs right. So this is another geometrical relation here. We're dealing with triangles. So A and B are they can't be negative for this type of problem, the way we're approaching it. So what is A? Card A is 5 feet from Q. A is 5. What is B? Well, we need to solve for LAP and then get LBP, and then we can get B. So 144 plus 25 square root of that, that's LAP. Pythagorean theorem. So $13. So that means that LBP is equal to 39 minus 13, 26, which means that B is equal to the square root of 26 squared minus 12 squared. $23.1. So B is 23.1. Now all we need is A dot. Well, we know that A dot is the magnitude of A dot is 2 feet per second, but do we put it as positive or negative here? Well, again, how do we approach this? We come back to our formula here, and this is all geometrical. So what is the cart A is moving in this direction. A dot at this moment is positive. B dot is negative. So we expect B dot to be negative. The length of this side here is decreasing, right? This is all geometry. You have to look at this equation. This was all geometrical, right? But this is like we equated two Pythagorean theorems in a way. Pythagorean theorem, that's triangles. The length of this side is increasing. A dot is going to be positive 2. And we expect B dot to be negative. So B dot is equal to, we got minus 5 and then 144 plus A squared and then times 2. So B dot is equal to plus 23.1 squared, second answer, times negative 5 times 2. Okay, divided by, negative 0.87. and that's going to be in feet per second. So, I mean, you can say that's exactly what we expect. This is getting smaller. It's moving in this direction. So, I mean, you could take off the negative and just say to the direction is to the left, but a plane flies horizontally at an altitude of 5 kilometers and passes directly over a tracking telescope on the ground. When the angle of elevation is pi over 3, this angle is decreasing at a rate of 5 or 6 radians per minute. How fast is the plane traveling at that time? All right. So we've got a tracking telescope. We'll just do like something like that. There's the telescope, and then we'll just put the plane anywhere. Something like that. Okay. The altitude is 5 kilometers. There's the ground. So the altitude is 5 kilometers. And the angle of elevation, I'm not sure what that is. So I'm sure you could ask your teacher what exactly is meant by angle of elevation. That's this angle. So theta, that's the angle of elevation. And so there's the height. Okay, so the plane is staying at this altitude. We'll call this x. That's, if the plane is staying at that altitude, then it's traveling in this x direction, parallel to the ground. I mean, I guess to make this clear, we could do, so this is x. But they don't give us any horizontal position, right? So I hope that our formula for the speed of the plane isn't a function of, we just want x dot. But if we have to find an x, I'm not sure what we're going to do. Let's see what happens. So I'm sure that's it's, we don't have to worry about x, right? Because like they don't tell us anything about the plane's horizontal position relative to the telescope or to something else. But what are we trying to find? How fast is the plane traveling? We're trying to find x dot, the rate of change of a position in this along this direction. But okay, they give us the rate of change of this theta. So let's relate. How do we relate theta to x? You know, this is x. So we say sine of theta is opposite, or no, tangent of theta is opposite over adjacent because we've got this opposite. So tangent of theta is opposite over adjacent. There we go. Okay, so we've got this equation that relates the two variables. Let's differentiate this with respect to time. So d dt tangent theta, that's going to be secant squared theta and then theta dot. Okay, d dt 1 over x, x is a function of t, so that's minus 5 over x squared, right? d dx of 1 over x is minus 1 over x squared times x dot. So now we solve for x dot. What do we get? X squared theta dot secant squared theta, we have a minus here, over 5. And actually we do have information about the position of x because we know the angle of elevation. So we can solve for x at this moment. So, okay, theta is going to be pi over 3. X is going to be 5 over tangent theta. So we're in radian mode. 5 divided by tangent pi over 3, 2.89 So x is equal to 2.89, and then theta dot is going to be negative pi over 6, because it tells us the angle is decreasing. Now, this is a little confusing. How are we using, so x is equal to 0 is the plane is just over the light. I mean, we just kind of arbitrarily set that up. How can we do that? You need to just focus on this miniature system we have here. Just focus on the system. You can imagine the system starts right when the plane is over or right when it passes over the tracking telescope. That's when our little system starts here. So, boom. When I say system, this system of lines and triangles, that's when it starts. So it starts. X is increasing. X is increasing. X dot is the velocity of the plane. This angle here and this triangle are all part of this system, right? We know how fast this theta is decreasing. So all we have to do is measure if the height of the plane is the same and it passes right over the tracking telescope, right? So it's like this, we don't have like an angle into or out of the page. Then all we got to do is measure, okay, if we have theta dot and we have theta, then we can, if we have a computer, we can calculate automatically how far ahead the plane is from the tracking telescope, like horizontally. We just did that. And so boom, we can get the speed. So minus, and then so So 3.5. What are the units? Kilometers and minutes. There we go. If we want to convert that to miles per hour, so kilometers per minute, there's 0.621 miles in 1 kilometer. There are 60 minutes in 1 hour. So 130 miles per hour.